Hello, viewers. In today's session, we are going to discuss a very important and conceptual problem from limits, right? And here we have this problem in which we are given a function f of x, which is defined as 1 minus e raised to lambda times greatest integer of pi minus sine raised to 10. And here we have greatest integer of fractional part of x for all x greater than 0, right? And for x less than 0, we are given f of x is equal to greatest integer of tan of fractional part of x minus 1. So let us see how we can solve this problem and how we can find out the value of this number lambda, which belongs to the set of real numbers, right? And here we are given that the limit of this function f of x, it exists when x tends to 0, right? And here the square brackets denotes the greatest integer function and the curly brackets denotes the fractional part function. So to solve these type of problems, we need to use the concept of greatest integer function and fractional part function. So we'll make use of the definition of greatest integer function and fractional part function, right? So we know that the limit of a function exists if the right hand limit is finite and it exists, right? So if the right hand limit is finite and it exists, and the left hand limit also exists and it is also finite, and moreover if both the limits, that is RHL and LHL, both are equal to each other at some point, x is equal to a, then we can say that the limit of the function when x tends to a, it exists, right? So to solve this problem, we'll first find out the right hand limit, then we'll find out the left hand limit, and then we'll equate both the expressions to get an equation in lambda, and then we can find out the value of lambda. So here our point A is 0, and here we have, say, x is equal to 0. So when we find out the right hand limit, we approach towards x is equal to 0 from the right of x is equal to 0, and we take a point in the neighborhood of x is equal to 0 and towards the right of x is equal to 0, and this point may be taken as 0 plus h, right? And when we find out the left hand limit, we approach towards x is equal to 0 from the left of x is equal to 0, and we take a point in the left neighborhood of x is equal to 0, and this point may be taken as 0 minus h, and here we have 0 plus h. So the notation for the right hand limit is limit x tends to 0, and here we put a positive sign, then we have f of x. So we take x is equal to 0 plus h, and here h is a positive quantity, and it lies between 0 and 1, and h is infinitesimally very small. So when x tends to 0, then h tends to 0, right? So now the right hand limit can be expressed in terms of h, that is the limit. Here x tends to 0 can be replaced by h tends to 0, and here we have f of x. So x is 0 plus h, so here we have h, right? 0 plus h is h, so here we have f of h. Now f of h can be written with the help of this expression, because here x is greater than 0, and when we find out the right hand limit, we utilize this expression for f of x. So f of h may be written by replacing x by h. So we have 1 minus e raised to lambda, and here we have greatest integer of pi minus sine raised to 10, and greatest integer of fractional part of x. Here x can be written as h, and here we have greatest integer function. So now we have to evaluate this limit. So here we have h tends to 0, right? And whenever we have the functions like greatest integer function and fractional part function, we cannot directly write h is equal to 0 over here. So we'll make use of the definition of greatest integer function and fractional part function. So we know that the fractional part of x is defined as x minus greatest integer of x. So here we have fractional part of h. So fractional part of h can be written as h minus greatest integer of h, right? Okay, now see, this h is infinitesimally very small, right? So this h is very small, so h is greater than 0, but it is less than 1. So the greatest integer of h is equal to 0. So here we'll write 0. So we have a fractional part of h is equal to h minus 0, that is equal to h, right? Okay, so now here we have greatest integer of h. So greatest integer of fractional part of h. So here we have fractional part of h, and fractional part of h is equal to h. So here we have greatest integer of h, right? Now greatest integer of h is 0. So now here we have 0, right? So this term, that is fractional, that is greatest integer of fractional part of h is 0. So now we have this limit h tends to 0. We have 1 minus e raised to lambda, and here we have greatest integer of pi minus sine raised to 10, and here we have 0, right? And sine 0 is equal to 0. So the sine raised to 10, 0 is equal to 0, right? So this term is also equal to 0. So now we have limit h tends to 0, 1 minus e raised to lambda, and here we have greatest integer of pi minus 0, right? Now see, this expression is independent of h, so we can remove this limit sign or the limit symbol. So now we have only this expression. So this is 1 minus e raised to lambda times greatest integer of pi, and we know that the value of the approximate value of pi is 3.14. So the greatest integer of pi is greatest integer of 3.14, that is equal to 3. So here we have greatest integer of pi is equal to 3. So now we can write 1 minus e raised to 3 times lambda. So the right hand limit of this function when x approaches to 0 is given by 1 minus e raised to 3 times lambda. So now let us find out the left hand limit. So the notation for left hand limit is limit, and here we have x tends to 0. We put a negative sign over here, then we have f of x. So when we approach towards x is equal to 0 from left of x is equal to 0, and then we have a point in the left neighborhood, that is x is equal to 0 minus h. So when x tends to 0, then h tends to 0. So now writing this left hand limit in terms of h, we can now write limit h tends to 0, and here we have f of 0 minus h. So now we have limit h tends to 0 and f of minus h, right? Okay, so now here we have the function that is for x less than 0, f of x is greatest integer of tan of fractional part of x minus 1. So now we have limit h tends to 0, and here we have the greatest integer of tan of fractional part of minus h, and here we have minus 1, right? Okay, so now let us take this expression, that is the fractional part of minus h. So we have just seen that the fractional part of x is equal to x minus greatest integer of x. So fractional part of minus h is minus h minus, and here we have greatest integer of minus h, right? Okay, now greatest integer of minus h. See, h lies between 0 and 1. So if we multiply this inequality throughout by minus 1, then we can see that we have 0. The direction of the inequality get reversed. So here we have minus h, then we have minus 1. So we can rewrite this inequality as minus 1, minus h, and 0. So this inequality indicates that minus h, it lies between minus 1 and 0. So here we have 0, here we have minus 1. So minus h, it lies somewhere between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1 by definition of greatest integer function, right? So now we have minus h, and here we have minus and minus 1. So this is minus h, then this is plus 1. So this is 1 minus h. So the fractional part of minus h is equal to 1 minus h. So now we can write the left hand limit as limit h tends to 0, and here we have greatest integer of tan of fractional part of minus h. So fractional part of minus h may be replaced by 1 minus h. So here we have tan of 1 minus h, and here we have minus 1, right? So now h tends to 0. So here we have tan of 1 minus 0 minus 1. So this is the tan of 1 minus 1, right? So the left hand limit is equal to a tan of 1 minus 1. So now we have right hand limit as 1 minus e raised to 3 lambda, and the left hand limit is equal to tan of 1 minus 1, right? Now since the limit of this function, it exists when x approaches to 0, so we must have right hand limit is equal to left hand limit. So now we can equate these two quantities. So we have 1 minus e raised to 3 lambda, then we have tan of 1 minus 1. So now we have an equation in lambda, and we have to solve it. So we can take this 1 to this side. So we have minus e raised to 3 lambda is equal to tan of 1 minus 1 minus 1. So this is tan of 1 minus 2, right? And now multiplying both sides by a negative sign, we have here positive. So this is e raised to 3 lambda, and here we have 2 minus tangent of 1, right? So now taking the natural log of both sides, we have log of e raised to 3 lambda, then we have log of 2 minus tan of 1, and this is 3 lambda log of e, that is log of 2 minus tangent of 1, right? So log of e is equal to 1. The natural log of e is 1. So here we have simply 3 lambda is equal to natural log of 2 minus tangent of 1, right? So we can now write lambda is equal to 1 over 3 times the natural log of 2 minus tangent of 1, right? So this is the required value of lambda. So viewers, here we have obtained the value of lambda as 1 by 3 and natural log of 2 minus tan of 1. So here it is interesting to note that if we take the approximate value of tangent of 1, this is tan 1 radians, and we know that 1 radian is approximately equal to 57 degrees. So tan of 1 may be taken as 1.55, right? So this is the approximate value of tan of 1. So tan of 1 is approximately 1.55. So substituting this value over here, the value of lambda can further be simplified. So we have 1 over 3, and here we have natural log of 2 minus 1.55. So now we can simplify it. 1 over 3 natural log 2 minus 1.55 is 0.45, and this is 1 over 3 natural log of 45 over 100, right? And if we reduce it into the lowest term, then we have here 5 times 9 45. This is 5 times 20, so we have 9 over 20, right? So this is the approximate value of lambda, that is 1 over 3 natural log of 9 over 20. Hello viewers, in today's session we are going to discuss a very important and conceptual problem from limits, and here we have to discuss this limit, that is limit x tends to 0 and greatest integer of x raised to 10 minus 10 divided by 20 minus greatest integer of x raised to 20. So here we have a very interesting problem, right? So what we will do here, we'll see whether the limit exists or not. So for the existence of this limit when x tends to 0 and we have this function, we have to find out the right hand limit and the left hand limit when x approaches to 0, right? And we'll see whether the right hand limit is equal to a left hand limit, right? So let us first calculate the right hand limit. So let us first take this function as f of x, right? So the right hand limit is given by a limit x tends to 0, and here we have a positive sign, and here we have f of x, right? So this is the notation for the right hand limit when x approaches to 0 from the right of x is equal to 0, because see here we have the point x is equal to 0, and when we approach towards x is equal to 0 from the right of x is equal to 0, then we have a point in the neighborhood of x is equal to 0, and that point is 0 plus h, right? This point is 0 plus h, and when we calculate the left hand limit, we approach towards x is equal to 0 from the left of x is equal to 0, right? And we arrive at a point which is in the neighborhood of x is equal to 0, and we say this point is 0 minus h. And remember, this h is a positive quantity, that is greater than 0 but it is less than 1, and h is infinitesimally very very small. So now here we'll take x is equal to 0 plus h, right? This point is 0 plus h, and 0 plus h is simply h. And when x approaches to 0, then obviously h approaches to 0. So now writing this limit in terms of h, we have limit h tends to 0, and here we have for x we can write 0 plus h or simply h. So we have f of h. So now we have limit h tends to 0, and f of h may be obtained by replacing x by h, right? So we have greatest integer of h, raised to 10 minus 10, and then we have 20 minus greatest integer of h raised to 20, right? Okay, so now here what we will do, we'll calculate the value of the greatest integer of h. Now this is an important quantity, and here we cannot directly substitute h is equal to 0 as we usually do while solving the problems based on limits related to algebraic expressions, right? So whenever we encounter greatest integer function or the fractional part function, we cannot directly substitute h is equal to 0 as such, right? So what we will do, we'll write the value of greatest integer of h, that is simply equal to 0, right? Because h is infinitesimally very small, and remember h is very close to 0, so it lies between 0 and 1. So the greatest integer of h should be equal to 0. So now we can write limit h tends to 0, and here we have 0, so we have 0 raised to 10 minus 10, and here we have 20 minus 0 raised to 20. So this quantity is 0, and we can now omit this limit notation because this expression is independent of h. It doesn't contain h. So we have simply 0 minus 10 over 20 minus 0, that is minus 10 over 20, that is equal to minus half, right? So the right hand limit of this function when x approaches to 0 is minus 1 over 2. Now let us find out the left hand limit. So the notation for the left hand limit is limit x tends to 0. Here we put a negative sign, then we have f of x. Now, when we find out the left hand limit, we take x is equal to 0 minus h. And here 0 minus h is minus h. And when x approaches to 0, then obviously h also tends to 0. So now we can write this limit in terms of h. So we have limit h tends to 0, and here we have f of minus h, because x is 0 minus h and this is minus h. So now we can write limit h tends to 0, f of minus h can be written with the help of this expression for f of x by replacing x by minus h. So we have simply greatest integer of minus h raised to 10 minus 10, and here we have 20 minus greatest integer of minus h raised to 20, right? Okay, so now as we have just explained, we cannot directly take h is equal to 0 in this expression, right? So what we will do, we'll first calculate the greatest integer of minus h which appears in this expression. So see, h lies between 0 and 1. So if we multiply this inequality throughout by minus 1, we'll get 0. The direction of the inequality get reversed. So here we have minus h, then we have minus 1. So we can again write this inequality as minus 1, minus h and 0. So this indicates that minus h, it lies between minus 1 and 0. So when minus h lies between minus 1 and 0, then the greatest integer of minus h should be equal to minus 1, right? So we should remember that greatest integer of h, that is positive h, is always 0, and greatest integer of negative h is equal to minus 1. So we have here limit h tends to 0. Here we have minus 1 raised to 10, then we have minus 10 here, then we have 20 minus minus 1 raised to 20. So now since this expression doesn't contain h, so we can remove this limit notation, and we are left with only this expression containing numbers. So minus 1 raised to 10 is simply plus 1. Here we have minus 10. Then we have 20 and minus. This is plus 1, right? So now we have 1 minus 10 is minus 9. And this is 20 minus 1, that is 19, right? So the left hand limit of this function when x approaches to 0 is minus 9 over 19, and the right hand limit we have just calculated that this is minus 1 over 2. So now we can see that although the right hand limit and the left hand limit both exist and they are finite, right? So these are the finite numbers, but here the right hand limit is not equal to the left hand limit, because minus half is not equal to minus 9 over 19, right? And for the existence of the limit of a function at a given point, the right hand limit and the left hand limit should be finite, and they should be equal to each other. So in this case, although the right hand limit and left hand limit are finite and they exist, but they are not equal to each other. So we can safely claim that the limit of this function when x approaches to 0, it does not exist.